Most people imagine space as a place where stars simply exist. They are just there, a bright point in the darkness, something permanent that has always been part of the sky. But stars are not decorations placed in the universe. They are objects that are constantly being created, changing, and eventually disappearing. And every new star begins in a place that looks almost nothing like a star. It begins inside darkness. Between galaxies and between stars, space is filled with enormous clouds of gas and dust. Astronomers call them molecular clouds. The name sounds complicated, but the idea is simple. A molecular cloud is basically a giant collection of tiny particles floating through space. Mostly hydrogen, the same element that became one of the first building blocks of the universe after Big Bang. These clouds are enormous. Some of them stretch across hundreds of light years. To understand the scale, imagine the distance from the Earth to the Sun. Light travels that distance in about 8 minutes. Now imagine a cloud so large that light will need hundreds of years just to cross from one side to the other. That is where stars are born, not in a bright explosion. It starts inside a cold, dark region where almost nothing seems to be happening. At first, a molecular cloud does not look like the beginning of everything. It looks like empty space. And this is one of the strange things about the universe. The most important events are not always obvious when they begin. A massive tree starts as a tiny seed. Human life starts as a single cell. And a star begins as a small difference inside the cloud. Some areas of the cloud contain slightly more material than others. Maybe another star explodes nearby and sent a wave through the cold. Maybe two clouds collide. Maybe gravity slowly created a small concentration of gas over a million of years. Whatever the reason, one region becomes a little denser. Gravity pulls things together. You experience it every day. It keeps you on the surface on Earth. It keeps the moon in orbit. It keeps planets moving around the sun. But the gravity has one important characteristic. Given enough time, it can create enormous things from almost nothing. A small amount of extra gas attracts more gas. More gas makes the region heavier. A heavier region creates stronger gravity. Stronger gravity pulls in even more material. The process begins slowly, then faster. The cloud starts collapsing. The word collapse might sound like something destructive. Usually, when we hear that something collapses, we think about buildings falling or structures breaking apart. But in space, collapse can be the beginning of creation. A star is born because matter falls together. The material that was spread across an enormous area begins moving toward one central point. As more gas gathers, the center becomes denser, and something interesting happens. The temperature starts rising. This might seem strange, after all space is cold. The average temperature of empty space is about minus 270 degrees Celsius. So why would a cloud of gas become hot? The answer is pressure. When you compress something, you increase the energy of the particles inside it. You can feel a small example of this with bicycle pump. Pump air quickly and the metal tube becomes warm. The same principle works inside a forming star, except the bicycle pump is replaced by gravity. And the amount of pressure is almost impossible to imagine. Eventually, the center of this collapsing cloud becomes what scientists call a protostar. A star that is not fully a star yet. This is the early stage, the moment before the engine turns on. A protostar is like a baby before its first breath. The ingredients are there. The structure is forming, but something important is still missing. The star is not yet producing energy through nuclear fusion. Inside the protostar, gravity continues pulling everything inward. The temperature rises higher and higher. The pressure becomes extreme. And finally, something incredible happens. The center becomes hot enough for hydrogen atoms to begin combining together. This process is called nuclear fusion. And this is the moment when a star truly begins its life. The star has turned on. Nuclear fusion is one of the most important processes in the universe, but it's often misunderstood. A star does not burn like a piece of wood. There is no flame, there is fire, and this is a chemical reaction. A star walks through something much more powerful. It changes the nuclei of atoms themselves. Hydrogen atoms combine and form helium, a tiny amount of mass disappearing during this process. And according to Einstein's famous equations, that lost mass becomes energy. That energy travels outward, eventually reaching the surface, then leaving the star as light and heat. The light can cross millions of years of space and finally reach someone looking at the sky. Our own sun went through this process about 4.6 billion years ago. Before the sun existed, there was only a cloud of gas and dust. The same basic material that later became the planets. The same material that eventually became Earth. The same material that would one day become living organisms, capable of asking questions about where everything came from. A star is not just a source of light. It's a factory. Factory that creates the conditions necessary for everything that comes after it. But the birth of a star is only the beginning. Once fusion starts, a new battle begins. Gravity is still trying to pull the star inward. The energy created by fusion is pushing outward. For a while, these two forces reach a balance. The star becomes stable. This stage is called the main sequence, and most stars spend the majority of their lives here, including our Sun. The main sequence is the longest and most peaceful chapter of a star's existence. A star can remain in this stage for millions of billions of years, but the length of this period depends on one thing: mass. How much material the star contains. And this is where stars become very different from each other. Because being bigger does not always mean living longer. In fact, the opposite is often true. A massive star has more fuel, but it burns that fuel much faster. Small star, like a person who carefully manages their savings. A giant star is like someone who receives a huge amount of money and immediately starts spending everything. The result? The giant may look more impressive, but it does not last as long. The life of every star is controlled by this balance. Gravity pulling inward, energy pushing outward. For billions of years, a star maintains this fragile agreement, but eventually every star reaches the same problem. The fuel begins to run out, and when that happens, the peaceful life of the stars ends. The next chapter begins. A star is born when fusion begins, but what exactly is happening inside it? From the outside, stars look simple. a glowing sphere in space, something bright that appears almost calm, but the surface of the star hides one of the most violent environments on the universe. Deep inside every star, atoms are moving at incredible speeds. Temperatures reach millions of degrees. Gravity is crushing everything inward with unimaginable force, and somehow, in the middle of this chaos, a star remains stable. For billions of years. The reason is a constant battle happening inside it, a battle between gravity and energy. Gravity wants the star to collapse. It has been doing this since the very beginning. Remember how the star was born? A cloud of gas started falling inward because gravity pulled everything together. That same force never stops. Gravity is always trying to compress the star. Without another force pushing back, every star in the universe would simply collapse into a smaller and smaller object. But stars have another weapon: energy. The energy created in the core pushes outward. For most of a star's life, these two forces balance each other. Gravity pulls in, energy pushes out. The star survives. This balance is called hydrostatic equilibrium. The name sounds complicated, but the idea is simple. A star is like a person standing still while two people push from the opposite sides. As long as the forces are equal, the person stays in place. If one side becomes stronger, the balance is broken. A star works the same way. If gravity wins, the star shrinks. If energy wins, the star expands. The entire life of a star is controlled by this invisible competition. But where does the energy come from? For a long time, humans did not know. Ancient people saw the sun giving light and warmth, but they had no idea what powered it. Some thought the sun was burning like a giant fire. That idea seems reasonable. After all, a fire produces heat and light. But there is a problem. A normal fire needs fuel. And even the largest possible fire made from ordinary materials could not keep the sun shining from billions of years. Something much more powerful had to be happening. The answer was hidden inside atoms. The core of a star is not a place where atoms sit quietly. It's a place of extreme pressure. Imagine taking the entire mass of the sun and squeezing it toward the center. The weight above in the core is enormous. The pressure becomes so intense that hydrogen atoms are forced extremely close together. Normally, tiny particles called protons repel each other. They are both positively charged. It's like trying to push together two magnets facing the wrong direction. They resist. But inside a star, the temperature and pressure become so extreme that occasionally these particles get close enough to overcome that resistance. Then something remarkable happens. They combine. Hydrogen becomes helium, and energy is released. This process is nuclear fusion. The word fusion simply means joining things together. In everyday life, joining things together usually does not create energy. If you put two pieces of metal together, nothing dramatic happens. But atoms are different. Inside an atom is a tiny amount of mass containing an enormous amount of energy. When hydrogen nuclei combine into helium, the final helium nucleus has slightly less mass than the original hydrogen. The missing mass is converted into energy. This is what Einstein described with the famous equation: energy equals mass times the speed of light squared. The amount of mass that disappears is incredibly small. But the speed of light is an enormous number. So even a tiny amount of lost mass creates a huge amount of energy. Every second, the sun converts around 600 million tons of hydrogen into helium. That number is almost impossible to imagine. 600 million tons every second. It sounds like the sun should run out immediately. But the sun is so massive that it has enough fuel to continue this process for billions of years. And even after all this time, it has only used a fraction of its total hydrogen. The sun is not a giant fire. It's a giant nuclear engine. A natural reactor built by gravity. The energy created in core begins a very long journey. A photon produced in the center of the sun does not immediately fly into space. The inside of the sun is incredibly dense. The photon constantly collides with particles, changing direction again and again. It's like trying to walk through a crowded room where every step sends you in a different direction. The journey from the core to the surface can take thousands or even hundreds of thousands of years. A particle of light created before humans existed may still be making its way outward, and eventually, after reaching the surface, it escapes. 8 minutes later, it arrives at Earth. The sunlight touching your face today began its journey long before human civilization existed. Stars are therefore time machines, not because they travel through time, but because they preserve the history of the universe. The light from a star carries information about what happened inside it, its temperature, its chemical composition, its age. By studying starlight, astronomers can discover the life story of objects that are impossibly far away. A star speaks through the light it releases, and we learned how to listen. But not all stars speak the same way. A star's personality is decided mostly at birth, and the most important factor is its mass. Mass is simply the amount of matter inside an object. Your mass determines how much gravity you create. The same is true for stars. A small star and a massive star may begin in a similar way, both from clouds of gas. But their futures will be completely different. A star like the Sun is considered medium-sized. It will live for around 10 billions of years. That sounds like an enormous amount of time, and it is. But first humans appeared only a few 100,000 years ago. The Sun has already existed thousands of times longer than our entire species. But compared with some smaller stars, the Sun is not especially long-lived. Small red dwarf stars can burn for trillions of years, longer than the current age of the universe. They are slow, careful workers of the cosmos. They use their fuel efficiently. They do not waste energy. Massive stars are the opposite. They are giants of the universe. They are brighter, hotter, but they live much faster lives. A massive star has dozens of times more fuel than the Sun, but it burns through the fuel at a much greater rate. It's like comparing a small candle with a giant flame. A giant flame is far more impressive, but it consumes everything much faster. A massive star may live only a few million years, a cosmic moment. This creates one of the biggest surprises in astronomy. The most powerful stars are often the ones with the shortest lives. In the universe, being bigger does not always mean lasting longer. Sometimes having more power means using it too quickly, and this difference decides how every star will end. A small star will slowly fade. A star like our Sun will transform into something completely different. A massive star will eventually face a violent ending. But before we reach the death of stars, we need to understand one more thing: the fuel inside them. Because a star's entire life depends on what it has left to burn, and eventually every star faces the same moment, the moment when the balance begins to break. The amount of material inside a star determines its entire future. A star's mass is like a set of rules written at the beginning of its existence. Those rules decide how hot it will become, how long it will live, and how it will eventually die. The smallest stars in the universe are called red dwarfs. They are not impressive when compared with cosmic giants. They are smaller and much less bright. If a massive star is a powerful sports car, burning fuel at incredible speed, a red dwarf is an economical vehicle designed to travel for a very, very long time. And that is exactly what happens. Red dwarfs use their hydrogen fuel slowly. They do not waste energy. They can continue shining for trillions of years. That is longer than the current age of the universe. Some of these stars, the born shortly after the first galaxies appeared, may still be in the early stages of their lives today. Then there are stars like our Sun. The Sun is not the largest star, it's not the smallest, it's somewhere in the middle. And this middle ground creates a very stable life. For around 10 billion years, the Sun will transform hydrogen into helium in its core. For most of that time, nothing will happen. The Sun will continue doing the same thing it has done for billion years, providing light and heat, supporting the existence of life on Earth. But eventually, even the Sun will change, because every star has a limited amount of fuel. The most fascinating stars are the giants. Massive stars can contain dozens of times more material than the Sun. They are incredibly bright. Some can shine millions of times brighter than our own star. Their power comes with a price. They live fast. Inside a massive star, the pressure is much greater. The temperature is much higher. And because everything is happening faster, the star burns through its fuel much more quickly. A giant star is not like a larger version of the Sun. It's a completely different world. This is one of the biggest surprises in astronomy. The most powerful stars are often shortest lived. A star with enormous energy may exist for only a few million years. A small red dwarf may continue shining long after the Earth, the Sun, and even our current civilization is gone. The universe does not reward size with longevity. Sometimes the brightest lights are the first ones to disappear. But mass does something else. It decides how a star dies. A small star will have a quiet ending. A medium-sized star, like the Sun, will slowly transform and leave behind a dense core called a white dwarf. A massive star will end in one of the most violent events in the universe, a supernova. An explosion powerful enough to briefly outshine billions of stars. The difference between these endings begins billions of years before the final moment. It begins when the star is still being formed. A star does not choose its destiny. It receives it at birth. The amount of matter gathered inside the first cloud of gas determines the entire story. In a way, stars are not so different from living things. The conditions at the beginning influence everything that comes after. But unlike humans, stars do not fight against their nature. They simply follow the laws of physics. And those laws lead every star toward the same unavoidable event, the moment when the fuel begins to disappear. For billions of years, a star can appear almost unchanged. The same light, the same steady energy, the same balance between gravity and fusion. But inside every star, time is moving forward. The fuel in the core is slowly being consumed. And eventually, even the most powerful engine in the universe begins to run out of energy. For a star like our Sun, this moment will arrive in about 5 billion years. By human standards, this is an unimaginable amount of time. But for a star, it is simply the next stage of life. During its main sequence phase, the Sun's core constantly converting hydrogen into helium. Hydrogen is the fuel that allows the star to resist gravity. But as this process continues, helium begins accumulating in the center. At first, this does not create a problem. The sun continues shining, but eventually, the amount of hydrogen in the core becomes too low. The engine begins to change. And when the core changes, the entire star responds. The first thing that happens is surprisingly simple. The core begins to shrink. Without enough hydrogen fusion, there is less energy pushing outward. Gravity starts winning the battle. The center of the star becomes smaller and denser. And as it compresses, it becomes hotter. This extra heat creates a new reaction. The layers surrounding the core begin burning hydrogen even faster. The star produces more energy. And that energy pushes the outer layers of the star outward. The sun will slowly expand. And it will become something completely different. A red giant. The name is almost too simple for what is actually happening. The sun will not just become a slightly larger version of itself. It will grow to a size that is difficult to imagine. The outer layers will expand hundreds of times beyond their current size. The calm yellow star that has warmed Earth for billions of years will become a huge, swollen sphere. Its surface will become cooler. Its color will shift toward red. The same star that once seemed perfectly stable will become a giant approaching the final stages of its life. This is one of the strange patterns of the universe. A star becomes larger when it's dying. For humans, aging usually means becoming weaker, but stars do not follow the same rules. When a star runs out of fuel in its core, it does not simply fade away. It transforms. Its final stages can be some of its most dramatic. Inside the red giant, the core continues becoming hotter. Eventually, the temperature becomes high enough for another type of fusion. The star begins combining helium atoms. Helium becomes heavier elements, such as carbon and oxygen. The star is creating new material inside itself. It's changing the ingredients of the universe, but in sun-like stars does not have enough mass to continue this process forever. Eventually, it reaches a limit. The core becomes unable to continue normal fusion reactions. The balance between gravity and energy begins to fail. The outer layers of the star become unstable, and slowly the star begins losing them. Imagine a person standing at the end of a long journey. leaving behind everything they carried with them. A star does something similar. It releases its outer atmosphere into space. The material spreads outward, creating a beautiful structure called a planetary nebula. Despite the name, it has nothing to do with planets. Early astronomers named them this way because some of these objects looked like distant planets through old telescopes. But they are actually the remains of dying stars. At the center of this expanding cloud, something remarkable remains: the core of old star. A small, incredibly dense object called a white dwarf. A white dwarf is what remains after the star, like the sun, has lost its outer layers. It's no longer creating energy through fusion. It's simply the leftover core of once active star, a piece of stellar history. A white dwarf is strange compared with normal objects. It can contain a large part of the original star's mass while being roughly the size of Earth. Imagine taking something as massive as the Sun and compressing it into a sphere the size of our planet. A teaspoon of white dwarf material would weigh an enormous amount. Matter behaves differently under such extreme pressure. Atoms are packed together in ways that do not happen naturally on Earth. But the story does not truly end there, because the material released by the dying star does not disappear. It becomes part of space. The carbon creates inside the star the oxygen, the elements produced during its life. All of them spread into the galaxy. And eventually, this material may become part of something new, a future star, a future planet, maybe even a future form of life. A star's death is not simply an ending, it's a transfer. The universe takes old material and uses it again. The atoms that once belonged to one star can later become part of another story. This process has happened countless times across cosmic history. Stars are born from the remains of previous stars. And in that sense, the universe is constantly rebuilding itself. But not every star receives a quiet ending. The sun will slowly fade into a white dwarf. However, the largest stars in the universe follow a very different path. Their deaths are not quiet. They do not gently release their outer layers. They end with one of the most powerful events known to science, a supernova. The most massive stars in the universe, and they lived with one of the most powerful events known to science, a single explosion that can briefly become brighter than an entire galaxy. But supernova is not just destruction. It's the final stage of the process that has been building inside a star for millions of years. A massive star lives differently from a star like our Sun. Because of its enormous mass, the pressure inside its core is extreme. The temperature becomes so high that the star can fuse heavier and heavier elements. First, hydrogen becomes helium. Then helium becomes heavier elements. The star continues creating new elements inside itself: carbon, oxygen, silicon, and eventually iron. For a while, the star continues fighting gravity. But iron is different. Iron is the point where the star reaches a limit. A star gains energy when it combines lighter elements into heavier ones. But creating iron does not provide energy in the same way. The process stops giving the star the support it needs. The balance that kept the star alive for millions of years suddenly disappears. Gravity, which was always waiting, finally wins. the core collapses. And it happens incredibly fast. In a matter of seconds, a core larger than Earth can collapse into an object only a few kilometers across. The energy released is beyond human imagination. The outer layers of the sun are thrown into space. The star explodes. A supernova is born. For a short moment, one dying star can release more energy than the sun will produce during its entire lifetime. But the most important part of supernova is not the explosion itself. It was the explosion creates. During the final moments of massive star's life, conditions become so extreme that elements heavier than the iron can form. Gold, silver, uranium. Many of these elements exist around us were created during the death of ancient stars. The universe needed stars to live, but it also needed them to die. Before this explosion happened, the universe was much simpler. There was hydrogen, there was helium, but there were no rocky planets like Earth. The ingredients were missing. Stars changed that. They took simple material and transformed it into something more complicated. Then, through their death, they spread those elements across space. The remains of one generation of stars became building blocks of next. After a supernova, what remains depends on original star. Sometimes the core becomes a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons on Earth. It's the crushed remains of star where matter has been compressed to an extreme state. A city-sized object containing more mass than our entire planet. But if original star was massive enough, even a neutron star cannot survive. The collapse continues. Gravity becomes unstoppable. The core disappears beyond a boundary from which nothing can escape. A black hole is created, the final transformation of the most massive stars. When we look at the night sky, we usually see stars as symbols of stability. Small points of light that have watched humanity for thousands of years. But every star is temporary. Some last trillions of years. Some exist for only a few million. Some end quietly, some end violently. But every single one changes the universe around it. The story of stars is not really a story about light. It's a story about transformation. A cloud becomes a star becomes elements. Elements become planets. Planets can become places where life appears. And eventually, that life can look back into the darkness and ask how it all began. The atoms in your body have traveled through a history much older than Earth itself. The oxygen in your lungs, the carbon in your cells, the calciums in your bones. In the universe, death is often the process that makes creation possible. The stars that disappeared billions of years ago left behind everything needed for the world we know today, including the ability to ask questions about the stars themselves. And this brings us to the final question: why do stars matter so much? Why should we care about distant objects burning in the darkness of space? Because the history of stars is not separate from our own. It's the beginning of our story. For most of human history, stars were something distant, lights in the sky, objects we could admire but never touch. Only recently we did discover the truth. Stars are not just lights. They are the reason the universe became capable of creating worlds like ours. The universe was young, and The ingredients needed for planets and life did not exist yet, but inside stars, nothing changed. Through nuclear fusion, simple elements became more complex, and when massive stars died, they scattered those elements across space. The material from one generation of stars became the foundation for the next. Again and again, the Earth was created from this ancient material. The rocks beneath our feet, the water in our oceans, the elements inside our bodies, and all of them have a history that began long before our planet existed. The atoms in your body were once somewhere else, inside ancient stars moving through space. This changes the way we look at ourselves. We are not separate from the universe. We are part of this process. The same laws that create galaxies and stars also created us. The same matter that only burned inside a star now think, dream, and ask questions about where it came from. A star spends millions of billions of years creating energy. Then, at the end of its life, it gives away a material it's created. The universe is constantly recycling its own story. When you look at night sky, you are not just looking at distant objects. You are looking at the process that also created you. Every star carries a story, and someone inside the story, a small part of our own. Because before we were people looking at the stars, we were the material that came from them. This is Void and Wonder, where emptiness becomes beautiful and science becomes a story.